So, systems that can arise, well, in a fully ordered system, I mean no disorder, we have a ferromagnet. If there is a disorder, we may have something like this with bond, topological, whatever. Then we have what is called an asperomagnet. The spatial distribution of moments in the ordered model, we have all the moments lining up. Here we have, they make a kind of a solid angle and different orientations. So the angular probability, here there is kind of a delta, it's certainty. Here there is a kind of angular distribution of values for the magnetic moment. This is the disorder ferromagnetic model. In an antiferromagnet, these are the simplest one, okay? In an antiferromagnet, we have this order model. Then in the disorder case, we have spiromagnets. The spatial distribution of moments here has two angular probabilities. Here we have two cones where moments are lining. And then two angular distribution probabilities, which eventually, if the disorder is very big and it can be even kind of a sphere. So this will be a line that will be impossible to distinguish anything. We can arrive to a system that is close to what is called a spin glass. Random exchange, frustrating interactions. This may lead to no magnetic ordering. Okay, and yet we have interactions. This is one. There are many varieties of what is generically called a spin glass. So just to give you an example of how disorder affects the magnetic properties, because there is no time in half a lecture to go over everything dealing with disorder, and particularly spin glass, it makes for almost one postgraduate subject. Let's see how chemical and site disorder can modify the magnetic properties of materials, but I am talking about very small amount of disorder. So I will show you examples which disorder is, the effects are the same. Only in the first case, we need a lot of disorder to make the effects visible. So what we are going to do is we have an antiferromagnetic lattice. This antiferromagnetic lattice, we substitute some sites randomly by a non-magnetic substitution. You will see how we do. But what we take is the antiferromagnetic lattice, and arbitrarily we just eliminate some moments in the lattice. In this case, I put 10% side dilution. There will be one example where I make higher dilutions, but the rest of the examples, the dilution is lower than 10%, maybe even lower than 1%. And yet, we will see the phenomena. Now, very important, in all these cases, in any case where you have to study in details properties, and is to define your experiment very carefully. Our experiment is going to be made in single crystal. So we will take a single crystal. We will orient the single crystal along the EC axis of antiferromagnetic alignment. So in our single crystals, the moments will be parallel and anti-parallel to the direction say, the Z direction in the laboratory. And that is exactly the same direction in which we apply the magnetic field. So our crystal, the antiferromagnetic alignment of our crystals will be parallel to the applied external magnetic field. Okay? Then, if anything happens with any canting, whichever it could be, we won't measure it. Of course, we did it, and we could not observe anything like that. But this is not our problem. So when we will measure spontaneous magnetization here in the problem I am going to show you, or in the experimental cases I'm going to show you. But don't think this spontaneous magnetization is coming because of a possible canting of the kind I explained to you. Because I am not measuring this direction. All the time I'm measuring this direction. Okay? But just for your information, I tell you that we also measure this direction and we found nothing. Okay? But don't be confused and just think we are measuring along the antiferromagnetic alignment axis. So the first example is manganese fluoride. Manganese fluoride has a rutile structure, very simple. It's an antiferromagnet. And the way we perturbate the antiferromagnetic lattice is substituting some manganese ions by zinc. Zinc fluoride is another rutile structure, isomorphic with manganese fluoride. So they both combine very well. So it is possible to group crystals with a certain percentage of zinc fluoride as substitutional impurity in the lattice of manganese fluoride. Okay? So manganese fluoride is a low anisotropy antiferromagnet. So it can be considered a Heisenberg antiferromagnet. You remember the first day, low anisotropy was in the extreme was the fully isotropic model, and I was telling you this is the isotropic model.